Hello everyone, it's Professor Fiore, and in this video we are going to be talking about multiband EQ, equalizers. Now before we get into this, you should be familiar with topics such as series RLC circuits, resonant EQ in general, and basic op-amp based simple gyrators. Now I've got videos on each of these. If you're not familiar, you can find the series RLC resonant circuit info in the AC circuit analysis playlist. And the other two, I have one on resonant EQ and one on a simple op-amp based gyrator in the op-amp playlist, right ahead of this particular one. Okay, so let's just jump in. What we're going to be looking at is a gyrator based version of a multiband EQ. There's several ways of doing it, but this is one popular way of doing it. So this is essentially made up of several resonant EQ systems that utilize a gyrator. Typically, you would see maybe 5 bands, 10 bands. That would be an octave band, also called an octave band EQ, or 31 bands, so a 1/3 octave EQ. That final thing, the 31 band, you would see primarily in professional circles. You'd see them for PA systems, tuning, control rooms, things like that. Now, each of the bands that you have would have a cut boost range of maybe 12 dB, 15 dB, as much as 20 dB, plus or minus. So you have a range of frequencies, and you can cut or boost in that region, right? So let's say plus or minus 15 dB. Each one of these bands is at a fixed center frequency, and the bandwidth or the Q of that is fixed, and it's designed in such a way that we don't have a lot of overlap between them, because we don't want, adjusting one band to have too much effect on the frequencies, on either side of it. So we have to kind of play with the Q as far as the number of bands we have. Obviously, if we have a 1/3 octave system, the Q is going to be much higher. It's going to be much tighter bandwidth than if we have an octave or, a 5-band, 4-band, whatever the heck we're going to make. Okay. Now, the way this is going to be set up, this particular design, the center frequency and the Q, they can be set by just 2 capacitors. Now, what's nice about that is you'll be able to then adjust your center frequency and your bandwidth by just scaling these 2 capacitors. And I'll show you exactly how that's done. The total number of op amps you're going to need for this would be the number of bands that you have. So if you're going to do an octave, it would be 10 bands plus 1. There's sort of a, let's call it a summing amplifier. It's not strictly a summing amplifier, but we have an extra one of those. And then I am not counting any input or output buffers that you might have, or other gain stages and things like that. Right? So if you want to do a 5-band, it's going to require 6 op amps. Right now, you might be thinking in terms of like quad op amps. This will really reduce the footprint of your design. Quad and 114-pin package, you can get 4 op amps. So you can make a pretty nice system, right? With very few chips. That's pretty nice. All right, so before we dive into the actual design, we have to take a look at our gyrator. So we're going to take a look at a simple gyrator. And what I want to plot here is the response of the impedance, right, the ohmic value versus frequency. So if you remember the way a series resonant circuit works, you get a dip at the resonant frequency, and then the impedance rises on either end. So if it's a series combination of a capacitor, inductor, and a resistor, right, at really low frequencies, the capacitor opens up, so you get a high impedance. At very high frequencies, the inductor opens up, so you get a very high impedance. And then right in the middle, the capacitive reactance and inductive reactance can cancel, and you're left with a very small value. So plotting this gives you something like a U shape, right, or a V shape, however you want to think of that. So you have this dip. Now we're going to use a gyrator because, inductors, especially for low frequencies, not the best things in the world. They're large, physically large, they're expensive. They don't behave all that ideally, so instead we're going to use gyrator, right? You can think of a gyrator as sort of a, a semiconductor-based, an active version, if you will, of an inductor, right? So, like I said, there's a separate video that discusses the gyrator in more detail, but I'm just going to throw out here a little circuit that, as designed, has a center frequency of just about 1 kilohertz, just a smidge over 1 kilohertz, and that dip impedance is just a little over 100 ohms, right? So just think 1 kilohertz, 100 ohms. How do I plot that? Well, there's a simple little trick you can do. I'm just going to take a current source, and I'm going to feed this circuit, right? This is the whole gyrator RLC simulated circuit right here. I'm just going to feed that current into there. So what ends up happening is, right, V is equal to I times R. So if I have a fixed current source, the voltage that I get out here, VF1 here in TINA, will basically echo what the impedance looks like. Now, the way TINA is going to do this is I'm going to do, up here in the analysis, I'm going to do an AC analysis, AC transfer characteristic. And what this is essentially going to do is take my output and divide it by the input. And it's going to give me a gain, right? I'm going to put gain in scare quotes there because it's not really a gain in this case. But it's going to be the voltage divided by the current. And of course, voltage divided by current is resistance or impedance, generally speaking. So I'm going to plot this from 100 hertz to 10 kilohertz so you can see basically what's going on here. All right. Bonk. All right, let's bring this down. Get a better look at it. Now, by default, TINA does this using a logarithmic axis over here, because normally if you're plotting gain, amplifier gain, that's what you want. But, I don't want some decibel version, log version of my impedance. I want the actual ohmic value. So just select the vertical axis here, go to properties, and change the scale from linear dB to straight up linear. And there you go. All right, so that you can see this big sort of U-shaped, V-shaped kind of thing. And we can verify what we have over here. Just grab a cursor, move this out of the way. And we'll just look for the dip. All right, so we just kind of come here and move around. And okay, well, right there I'm getting 105 ohms. It's 1.07 and change kilohertz. So like I said, think about 100 ohms at 1 kilohertz. That's what we're looking for. All right. As we go to lower frequencies down in the bass or higher frequencies up here in the treble, you can see this is getting pretty big. Right, we're several k ohms. If you took it further down into the bass, 50 hertz, 20 hertz, you'd be looking well over 10K at that point. All right. Okie dokie. So how are we going to use this as part of this cut boost system, right? I mean, this by itself, it's just, if you maybe put a resistor over here and this was a voltage source, you would have a fixed filter. This is how you make, well, one way of making a notch or band reject filter, right? It would be fixed. You wouldn't be able to adjust it. So what we do is we're going to take this and add another op amp, and we are going to come up with a single band gyrator-based resonant EQ. So this right here is the circuit we were just looking at. This is our 1 kilohertz, 100 ohm dip circuit, okay? And up here we have an op amp. This is essentially set up as kind of like a differential amplifier. You can think of it that way. Here's our feedback resistor, RF. Okay, and then I have this input resistor, R4. How does this work? Well, the pot is where we're going to get some of our adjustment, right, for the amplitude. And we're going to look at two extremes here, and that's having the pot way over here on the left and the pot way over here on the right. So starting off on the left extreme, this wiper arm is connected right to here. So basically what we have right up front before we even get to the op amp, this op amp number 1, what we have is a divider, a voltage divider between R4, a fixed resistance, and our series RLC circuit, right? So yeah, I know there's an op amp here, but just remember this thing simulates an inductor. This is just an RLC circuit. In your mind, just think of a series RLC circuit here. So I've got 1K, and then I've got this other impedance out here that has that big U shape. What does that do? Well, at really low frequencies and really high frequencies, the voltage divider effect is minimal, right? You got 1K over here, you got maybe, 5K, 10K, whatever it is, right? For this RLC at the really low and really high frequencies. So you get virtually, whatever VGen is, that's what you get over here. And then that will be applied, right, to the input of the amplifier. What's the gain of the amplifier? Well, the gain of the amplifier is going to turn out to be about 1. Here's your RF and your RI. Now, you got a 10K over here, and then this is attached back to the source. So remember, the gain of a non-inverting amplifier is RF over RI plus 1. So you got 1K, you got 10K plus for this stuff, right? That's going to work out to just a smidge over unity, okay? All right, so essentially what ends up happening is you get the loss from the RLC network in R4, and then that goes through a gain of 1, so you get whatever the loss is. Now, on the other hand, if the wiper arms are over here, then that combo, that RLC combo, basically is the RI. And now you're going to get a lot of boost, because remember what we said, that's a 1K ohm, at 1 kilohertz, that's about 100 ohms. So now you have an RF of 1K, you have an RI of about 100, that's going to give you a gain a little over 10. Okay, so we're going from about 1/10, 1/11th to be a little bit more accurate, to a gain of about 10, again, 11. So we're looking about minus 20 dB on this end and about plus 20 dB on this end, right? So you put the wiper arm way over here, you get a big cut, about 20 dB. You put the wiper arm way over here, you get a big boost, about 20 dB positive. Hey, if you put it in the middle, basically you're going to get a little bit of both. You're going to get some loss and some gain. It's going to cancel out, and you're going to get 0 dB, pretty much right at dead center. And as you go off to either end, you're at 1/4, 2/3, whatever. We're going to get something in between. All right, so let's go check our pot. Right now, I've got this set at 100%, right, compared to our little knob over here. So that means the wiper arm's way the heck over here. And we'll just do an analysis. We'll see what we get. All right, so once again, I'm going to do like a Bodie plot. Ooh, look at this. Okay, so this is our peak. We can see there's 1 kilohertz. Okay, that's just beyond 1 kilohertz like we expected. And just like I said, a little over 20 dB. So here's our 20. We can see the peak is just a little tiny bit beyond that. Looking good. Now let's go back and set this up to 0. So now the wiper arm is all the way to the extreme left. We'll redo this. Bonk, same deal, all right? There's our 1 kilohertz. We can see it's just beyond minus 20 dB. All right, so when you're designing this, basically, if you didn't want plus or minus 20, you wanted plus or minus 15, let's say. You just have to monkey with the value of R4 and the value of R3. And normally you'd set these to the same value, right? And as you go up and down, you get more or less peak gain. All right, what happens if we're, somewhere in the middle, right? So what if we're at, I don't know, how about 90%? Okay, so we should get some boost, but not 20 dB worth. And sure enough, there we go, right? So now we're looking at not quite 5 dB, okay? So we get the extremes at the end of the pot, right? At the end of the pot movement, we get the extreme high values, right, of either boost or cut, right? Don't worry about this little rise out here. Here's 20 kilohertz right here, right? So that's your audio range. Now, how do I adjust? How do I go about changing the center frequency or changing the width, the Q of this? All right, well, basically we're going to focus in on C1 and C2. If you change both of them by the same amount, for example, if we were to divide them by a factor of 10, so that this is 22 nanofarads and this is 1 nanofarad, you would wind up scaling the frequency by a factor of 10. Right? So, small caps, generally you think in terms of high frequency, right? Big caps, low frequency. So that's exactly what we're going to see here. If you want to adjust the Q, then you adjust the ratio of C1 to C2. So the bigger C1 is relative to C2, the sharper the Q, all right? So, one way of thinking about this is you can kind of think of like two overlapping sort of responses, like a low-pass response and a high-pass response. And C2 is essentially setting the curve like over here, and C1 is setting the curve over here. So if you bring them in, right, if you bring them closer together, you get a tighter Q. So what I mean by that is if you were to, let's say, increase C2 by a factor of 2, you would decrease C1 by a factor of 2. All right? The end result would be you'd have the same exact critical frequency. You have to use the same ratio. Factor of 2, factor of 3, factor of 1.7, factor of 1.1, whatever the heck it is. Whatever you multiply one by, you divide the other one by, and that'll maintain your center frequency. It'll just change the Q. All right? Cool. Okay. So you're going to need to adjust those ratios depending on, again, the number of bands you want, because you don't want too much overlap on these things. Okay? But you don't want it to be too narrow, because then there's going to be, frequencies that you're not going to be able to affect. So, you have to kind of, pardon the phrase, balance that out. All right. So, that's all well and good. We, of course, want to do multiband. This is just one band. How do I do, 5-band, 10-band, whatever? Well, let's just take a look at one step up. All right, let's go to 2 bands. So here's the original circuit, and all I've done is I've added another gyrator RLC system. All right, so here's our first circuit. You can see all I'm doing is I'm just cloning this, copy and paste, basically. And what I've done, as I just mentioned a moment ago, is I've taken the capacitors and I've scaled them both down by a decade, by a factor of 10, right? My 220 became 22, my 10 became a 1. So that should translate my frequency up by a decade. So from 1 kilohertz, this should be 10 kilohertz. But because this ratio, right, between these two capacitors is still the same, it's, 22 to 1, or 1 to 22, however you want to think about it, the Q should be roughly the same as what we had over here. Okay? Still have the 10K pot. Let's see what we have for settings. So I've got 90% on this. We already saw what that looked like. And then I've got 70% on this. So I should get a little bit of a boost, like we saw last time, down at 1 kilohertz, and a smaller boost, because this was only 70%, smaller boost up at 10 kilohertz. And off we go. Oh, and there we go. So here's our 1 kilohertz, right? You can see that big boost, relatively big. And then here's 10 kilohertz, and you can see how that's punched up a little bit, right? The other one kind of went like this. So I think that was this one. Right. All right. So by punching up that second one, right, we're getting a little bit more up there. All right. But we can do, other sorts of things. For example, I could say, let's bring this down to like 20%. So now we're going to have a cut at 10 kilohertz. Still have the boost at 1K though. All right, so there's our 1K boost. And then, that was, like I said, 20%, so it's not a huge amount, but we are seeing a cut, and you can see that's right around 10 kilohertz. Okay, so the Q that I have set up here would probably be too fat. If you want to do a 10 band, you'd have to tighten this up a little bit. This might work fine for like a 5-band. Certainly it would be lousy if you're going to do a 1/3 octave, but the idea here is just to show you how this whole thing works. Okay. How do you get the other bands? You just keep copying and pasting, right? So next band, take the same thing, pop it over here, take another one, and you just keep taking this circuit and you add more and more and more, and you just have to play with these values, all right, to get the new frequencies. And like I said, you're going to have to adjust them anyway to get the Q that you need for however many bands you have. But that's it. So the total number of op amps you need is the number of bands you have plus 1, not including an input buffer and possibly an output buffer, okay, or a gain stage, whatever it is that you're needing in that case. All right. So again, something like a quad op amp can come in really handy over here. 3 quad op amps, right? That's 12 op amps. So you could make a 10 band and have, another op amp kicking around for your input buffer, right? To isolate your source from the whole circuit. That works out pretty well. All right. Now, a couple of tweaks, a couple of little things. One of the practical issues is, capacitors only come in certain sizes. Typically, you're looking at like 5% tolerance for standard values. So how do you get the center frequencies that you want? And there are standard center frequencies. ISO standard center frequencies start at 1 kilohertz. So if you're looking at octave, it goes up by factors of 2. So the standard center frequencies for a one octave 10 band graphic equalizer would be 1 kilohertz, 2 kilohertz, 4 kilohertz, 8 kilohertz, 16 kilohertz working up, and then working down, right? You would go from 1K to 500 to 250 to 125, 63, 31, right? And there you go, okay? And then there's in-between values if you're going to do 1/3 octave, right? And then you would skip every other one of those that I mentioned if you were doing like a 5-band, all right? But the issue remains, right? You can't specify. You can't go to the store, go online, and get a 229 nanofarad capacitor if that's what you need. So there are some things you can kind of tweak a little bit, right? So R1 over here, along with R2, can be used to slightly tweak the Q and the resonant frequency. As a matter of fact, sometimes you'll see circuits where they say, I'll put a pot in here, maybe a pot with a series resistor. And they'll say, oh, you can use this to, adjust your center frequency. Well, yes and no. The problem is adjusting this resistor or this resistor will change the center frequency, but it will also change the Q. So, that's probably not exactly what you want. If you were to increase R1, F0 will go down, but your Q will go up. So, if you try to do a wide range on that, that's going to be really kind of funky, to have your Q expanding and contracting while you're changing the frequency. Small amounts, though, that might be just enough. If you need a 98 k ohm resistor, for example, you can find that. It's easy to find 1% tolerance metal film resistors, and they're relatively inexpensive. You can do something like that just to tweak, just to compensate for the fact that you have, a limited range of standard capacitance values, right? So you can kind of tweak things that way. Another option is to, use pairs of capacitors. If you needed like a 229, let's say, you could put very closely, you could put a 10 nanofarad in parallel with this, right? Caps in parallel add up. So you could do something like that too, if you really, really wanted to, nail it. So you do have some options there to deal with. Generally speaking, as far as caps are concerned, the quality of the components, I would suggest at a minimum, you're going to use polyester, mylar capacitors. It's a good economical choice. Stay away from aluminum electrolytics. If you need some larger capacitors for lower frequencies, stay away from those. Those are not good for this kind of application. Polypropylenes, if you can afford them, would be nice. Physically large, expensive, but a really, really nice dielectric. I would probably recommend using metal film resistors just because it's modestly more expensive than carbon film, and you get lower noise. It's a very nicely precise, controlled resistance. So yeah, let's go with that. All right. And of course, the pots, you can get rotary pots if you want to save on the front panel. But typically, graphic equalizers use sliders, right? They use slide pots. So it just looks nice. You line them all up, and it kind of shows the frequency response that you get, right? It kind of echoes their frequency response. All right, so you just add this out. Just keep cutting and pasting, so to speak. Easier to do on the computer than it is on a PC board, but there you have it. Okay, any questions? Put them down in the comments, and we'll see you next time.